Good morning, one and all. I'm here to present my paper ID 130 Evaluation on Radiation Exposure in Human Eye Tissue Model with Inverted F Antenna. Myself, Jemima Priyadarshini, Research Trainee, Emmanuel Hospital, Avadi, Chennai. My co authors are Dr. Emmanuel Nargunathan, Dr. Anita Christie, and Kanimuriye. The agenda for today's presentation includes motivation, objective, SAR estimation, results, and conclusion. The introduction of this paper deals with how human beings are susceptible towards the radiation absorption either through non-ionizing sources or ionization sources. Now, if you see non-ionizing radiations that are constantly emitted by a base station, mobile phones, and laptops, various devices that are proximal to human beings, our concentration is towards this non-ionizing, the long-term exposure, and we are assessing this exposure with the devices that we are keeping near us. The motivation behind this paper is the effects that are caused due to this radiation. For example, if a person is using a continuous mobile phone, the long-term effects includes the alterations in brain functions, hearing ability, leakage of albumin, and when you keep a mobile phone near you and you sleep, there is a change in your alpha, beta, delta waves or in the brain waves, and there is also cases where there is a severe phantom pain that occurs due to the radiation absorption caused due to mobile phones. The objective of this paper is to develop an eye model with a tissue equivalent dielectric material to interact with an inverted F antenna that operates around GSM 900 MHz frequency and to investigate specific absorption rate. So why do we go for an eye model list? Previously, we were using mobile phone only for hearing purposes, so it was kept proximal near our ears and a phantom. But it is not the case nowadays because we keep the mobile phones in front for FaceTiming, for online classes, and so many applications or uses the face recognition. All these things where mobile phones are kept proximal towards the face. So we need to study how eye tissues are affected due to this radiation. We are using inverted F antenna because it is one of the antennas that are simple and that are widely used in mobile and also in applications such as laptops. What is SAR or specific absorption rate? It's a measure how much electromagnetic energy is absorbed by a biological tissue when exposed to radiating devices. For example, it may be any devices, and mobile phone is a prominent example where SAR can be in terms of a power with a power, or in terms of electric field, or in terms of current density. Our focus is on terms of conductivity of the tissue, electric field, and the mass density. The module of this paper has three components. One is the dielectric properties, then inverted F antenna that operates around 900 MHz. Then we go for computation of SAR and results and discussion. So first thing is to check the radiating source, whether the design properties of the radiating source. We are considering the inverted F antenna. So IFA has three components, that is a rectangular element that may be a wire or a planar. We have a short circuiting plate and a feeding arm. Now, when you see the right side picture, that is designed using the designed using the CAD-FICO tool, where we observe that we have a feeding arm, a rectangular plate or a rectangular element, and also a short circuiting plane. Now, for every frequency, there is a design parameters based on the design equation. For 900 megahertz, we derive the design parameters of the IFA, and we obtain the dimension of the planar arm, folded arm, and feed arm, and offset position. And based on these values, we are designing the inverted F antenna on a ground plane. Now, once I design an antenna, I need to check whether my antenna is operating or not. So in order to check, two things very important is whether the gain of an antenna, we should have a considered amount of gain, and also it should operate at a particular range of frequency. So for which we estimate, for inverted F antenna, we observe that the radiation, it's like a cut donut shape, and it's like a radiation, the gain is around 2.8 dB, and we also see that it operates in the range of 0.9 gigahertz, that is 900 megahertz. We have so these two pictures clearly indicate that the antenna that we have designed is operating at 900 megahertz for a reasonable gain. Now, coming to the other side is to design an eye tissue. So we need to know what are the tissues that are available, primary tissues that are available in eyes. So we observe that we have cornea, Then we have this white layer of our eye, that is sclera, that is a protective layer. Then we do have a lens, which is like a capsule that encloses both the lens nucleus and also cortex. And we do have an inner chamber, that is a vitreous chamber with the vitreous humor fluid. Now, considering these tissue structures, we go for a biomedical database where all the tissue properties are available. We are extracting the tissues like eye tissue properties for 900 megahertz. Camilla Gabriel has already compiled the dielectric properties. We derive these properties, and based on these properties, we design the linear eye structure. Now, the properties we have taken, the tissues for which the properties we have taken is cornea, sclera, vitreous humor, and lens cortex. We see each value have different permittivity and conductivity values. So, once we obtain these values, we place a linear tissue model above the inverted F antenna, and we observe the radiation characteristics. So when we observe the radiation field characteristics, so initially we saw it as a donut shape without the interference of an tissue structure. Now in all the tissue structures, we see there is a change in the far field characteristics. The radiation pattern, 3D pattern tends to change, and also it is observed that the gain also tend to change in each cases. So our gain was 2.8 for an inverted F antenna. It varies between 2.5 to maximum of 3. So it shows that when I place the tissue above the inverted F antenna, in all scenarios, my antenna is functional and there is a radiation emission occurs. So obviously, I can go for calculation of specific absorption rate. Next is comparison of the gain. As I said earlier, it is between 2.5 to 3, and we see cornea has a less gain comparatively and sclera has the maximum gain. Now, the second thing to verify whether our experimental scenario is working is to check the return loss. So, what is return loss is how much input that I have given, it should radiate, it should not be reflected back. So, minimal reflection and maximum radiation is termed with the parameter called as S11. It is also called as return loss parameter. So now we are considering the return loss for all the cases like cornea, vitreous humor, sclera, lens cortex, and lens nuclei. We observe that we get a decent amount of return loss. That means it is operating at its maximum potential around minus 27 to minus 36 dB. In this case, we see lens cortex as a maximum return loss. That is maximum return loss. So it operates more under this condition. Now, the primary focus of this entire paper is SAW calculation, estimation, and its discussion. Now, when you see, we are taking a range of 0.6 gigahertz to 1.2 gigahertz, and we are estimating specific absorption rate for over the frequency range and for each tissues. Once we calculate the tissues, we observe that its maximum between 0.85 and 0.9, and specifically at 0.85 gigahertz. We observe that cornea has a maximum radiation absorption around 44.211, and we also observe that the minimal value is lens nuclei has a resistance towards absorption with minimum of 32 milliwatts. And we see the next to cornea, we do observe that vitreous humor, that is the inner portion of the eyes, also has a maximum absorption, and other lens cortex, and that is all coming in between these values. Now, what do we infer is we observe that each tissue has different medium characteristics contributing to different SAR values. Cornea medium tends to absorb more radiation, that is 44 milliwatts, and followed by vitreous humor 42. Lens nucleus has a resistance that is around 32 milliwatts per kilogram. Sclera absorbs more, but still it's less than the cornea or vitreous humor. Now, the entire paper can be summed up with a discussion on we just develop a homogeneous linear eye model, and we design for evaluating using MOM method in FICO. So we are using a CAD FICO tool, which is called as Altair's HyperWorks FICO. Here, the reflection coefficient is estimated, that is, it's been minus 24 to minus 36. And we also see that the IFA is operational and it's optimal with a gain of 2.5 to 3 for all the eye tissues. And there is a maximum SAR value near the band of 850 to 900 megahertz with 44 milliwatts per kilogram for cornea and minimum of 32 for a lens nuclei. To sum up the entire paper is we have investigated the human eye tissues at 900 megahertz. There is an essential conductive and permittive properties applied. So it's possible to develop a numerical model for human beings, and we can go for estimating the radiation absorption. And we go for a homogeneous model for for cornea, sclera, vitreous humor, lens cortex, and lens nuclei. Then a peak SAR and also field parameters of far field are calculated for analysis. So this method can also be extended not just for eyes, because we don't place a mobile phone near just on the near the face. We do keep it on various parts of our body, so we can go for an extended analysis where SAR exposure through the human body, and it can be done detail in future. Thank you for this opportunity, and if there is any clarifications, please reach me at mailjemmy@gmail.com. Thank you.